Alright everyone, we have a L'Hopital rule problem which involves a product between two functions, sine of x, natural logarithm of x, and we want to find what happens to the limit as x approaches 0 from the right hand side. Now, the sad thing is, when you're doing L'Hopital's rule with natural logarithm of functions, if you're taking the limit of x of a natural logarithm function as it approaches 0, that's going to hit a discontinuity, as you see here. This is the natural logarithm function, and if I approach from the right, it's going to reach an asymptote. That's always going to be bad news. Discontinuities are always going to flummox us up. And this is indeed an indeterminate product, sine of x times natural logarithm of x. We would like to think that we can have the freedom to choose which factor we want to put as a function divided by 1 over the other function. We'd hopefully like that we could do this, that this could be either rewritten as natural logarithm of x divided by 1 over sine x, or sine of x divided by 1 over natural logarithm of x. But unfortunately, there's only one method which really avoids us the most pain and allows us to solve this problem the quickest method. And that problem is, I credit to Ms. Shaw Maths, who's done this. Thank you very much. And that involves taking the reciprocal of the function sine of x. Now, before we proceed further, I'd like us to gain an intuition, like a cheat sheet, if you will, on what the answer of this limit is going to be. It's going to be 0. I graphed this function on Desmos over here, sine of x times natural logarithm of x. And given the fact that natural logarithm of x cannot be defined for any negative number, it would make sense that the left-hand side of the graph, to the left of the origin, is completely undefined. So you basically get a trigonometric function that kind of grows in terms of its amplitude, but eventually reaches a steady amplitude and it keeps going like that at the same period. So the way we do this, as Ms. Shaw suggests, is take the limit as this x approaches 0 from the right hand side of natural logarithm of x divided by 1 over sine x. And that is simply cosecant of x. I really hate these reciprocal trigonometric functions. They're pretentious in the literature, in my opinion. And I think Blue One Brown shares the same opinion as well. But yeah, that's what we'll have to do. Now we go to the L'Hopital one time. Take the derivative of this. That's going to be 1 over x. And derivative of cosecant of x, that's going to be minus cosecant of x. Cotangent of x. Just from looking at the appendix in a typical calculus book. Now here is where we undo the pretentiousness of this notation and rewrite this in terms of sines and cosines. This is going to be 1 over x divided by minus, 1 over sine x times cosine of x divided by sine x. And now if we apply our rules for dividing a fraction by a fraction, we know that we'll multiply 1 over x by the reciprocal of what's down here at the bottom. So we get 1 over x times minus sine x sine x cosine x. And now I'm going to do something kind of, wait, I don't think that's right. Yeah, I knew it. The cosine x goes at the bottom. And now I'm going to do something very sneaky here, because actually this sine x over x, that's actually a famous function with a very famous limits as you take it, as you take x and have it approach 0. So I'm going to rewrite this as limit of x approaches 0 of sine of x over x, don't forget the minus sign over here, sorry about that, times limit as x approaches to 0 of sine of x divided by cosine of x. Now for the squeeze theorem, you can rigorously show that sine of x over x as x approaches 0 from any direction is always going to be 1. Squeeze. That's the nice thing about unit circle periodic. That's the good thing about periodic trigonometric functions. They're always bounded on top and below by 1 and minus 1, so we can make these squeezing arguments for things like that. But for exponents and natural logarithm functions, you unfortunately can't do quite the same. So, yeah, let's see. I have 1 over here. This is multiplied by sine of x over cosine of x. We look at the behavior as this goes to 0. That's quite easy. That's just sine of 0 and cosine of 0. So that becomes 1 times 0 over 1, which just becomes freaking 0. And that is exactly what we wanted over here. It will become 0. And yeah, that's it. You're done. But again, I like there being freedom of choice in what you're being able to do, and I would like to show you how, very sadly, if you do the second attempt of rewriting this as sine of x over natural logarithm, sine of x over 1 over natural logarithm of x, and you attempt to L'Hopital that, you're unfortunately going to go through some very nasty repetitive problems. And I'll show you how that happens. So, method 2, attempt 2. Take the reciprocal of ln of x. So I'm going to rewrite this completely as, this is attempt 2 now. Limit as x approaches 0 from the right hand side of sine of x 1 over ln x. And if we go to the L'Hopital by ambulance one time, this becomes cosine of x minus 1 ln x squared 1 over x. And now we're going to do something very similar to what we did in the previous problem, which was apply the compound fractions swapping trick. So this is cosine of x divided by another fraction. We're allowed to take the x and the ln of x squared and bring it up to the numerator. So this just becomes minus cosine of x, x, ln x, ln x. 2 factors of ln x. And now here's a surprising fact. It actually turns out that, I'm going to factor out the negative in front because we can. The limit as x approaches to 0 from the positive side of x ln of x, that's actually, when I say will be tolerable, and it actually becomes 0, as we just stated. But then you're also left with, here I'm just applying that the limit of a product is a product of the limits over here. So the limit as x approaches 0 from the right hand side is cosine of x ln of x, which is basically a function that is almost similar to this. In fact, you can almost understand that like cosine of x is really sine of x just horizontally translated by pi over 2 units to the right. So then this becomes ln of x sine of x minus pi over 2. Yeah, or pi over 2 minus x. I hope I got the order correct. But yeah. And that thing is L'Hopitalable. If you were to rewrite the x, natural logarithm of x, as natural logarithm of x over 1 over x, and then thanks to Jim H. on Socratic.org, you show that this also, by another trick to the L'Hopital, becomes 0. Can you see now why I don't find the second method to be worth it? Not only do you have to take yet another trip to the L'Hopital for this particular factor over here, for this factor, you end up with something that's already similar to this thing here, but it's not quite the same. And also, if you plug in 0 into there, natural logarithm of 0, sine of 0 minus pi over 2, that's still an indeterminate form. You're going to take natural logarithm of 0, so we're still going to get infinity times 1 minus sine of pi over 2 is minus 1. Now, it's not necessarily an indeterminate form, but when we had it as cosine of x, if we had this as cosine of x, it would be 0. Oh wait, no. Cosine of x goes to 0. Yeah, it would be 1. Yeah, no, this whole thing is infinity, and this thing is minus 1. Yeah, that's good. So we would still, this whole thing would still come out to be a form of 0 times infinity, which is still an indeterminate form. Might be overthinking it here, but like, yeah, that doesn't, when I go and check the process, I think like, oh, this is still indeterminate, so I don't feel like we're done with the entire thing, especially if this side tends to go to infinity. So it's really inconclusive if you go through it through this approach. So unfortunately, Fishaw's method wins out in the end, in my opinion at least. But I would like to go through at least both methods. This is how you go and check which one you prefer. And yeah, limit as x approaches 0 from the right hand side of x, ln of x. I can do that another time, but basically you have to take the derivative of the top here, derivative of the bottom here. I think just once is enough, then take that as x approaches 0, and you get, boom, it becomes 0. So yeah, you kind of get that same result as well. Anyhow, I think I've gone on for too long. So the moral of the story overall, when taking limits to 0, and you have an ln of x, you want to get rid of that. Yeah, let me repeat that again. If you're taking a limit when x approaches to 0 from either side, and you see a natural logarithm of x for L'Hopital problem, use the derivative to get rid of that thing as fast as possible. Differentiate away is what I say. That's the moral. And I think that's a good place to end off at. So please feel free to like, comment, subscribe, and offer suggestions on what I could do to make the quality of the video better. Otherwise, I'll see you in the next round.